In Unit 2, we are going to learn about the derivative. And the derivative is one of the most fundamental ideas that we're going to learn about in all of calculus. And so our goal for today is just understanding what is a derivative and how do we find it. And to go back to geometry, something you learned in your geometry classes, and you probably learned this when you were talking about circles, is that if we were to choose 2 points on a circle, and draw a line that goes between those 2 points or intersects those 2 points, we would call this a secant line. So the line segment between the 2 points is a chord, but the line itself is a secant line. On the other hand, if we picked a point on our circle and we drew a line that only intersects the circle in that one place, that one point, so it like touches the circle but doesn't go through the circle at 2 points, this is what we would call a tangent line. And so when we talk about a secant and a tangent line, these don't have to be, this terminology is not specific to circles, but that's where you would have heard of it before. So a secant line, again, is determined by 2 distinct points. And so a topic that we learn about in algebra is finding the slope of a secant line. So on our curve of this function f, let's imagine that we have a point, and we'll say this point is when our x value is a. So our output or our y value would be f of a for this first point. And let's make a second point on our curve. And I'm going to say this is when x is b. So our output or our y value would be f of b. And if we were to draw the line that goes between these 2 points, that intersects these 2 points, we could call this the secant line of f. And even though it intersects, I said it intersects these 2 points locally, it's okay that it crosses our curve again in another place. We're really just looking for where this line crosses f between these 2 points a and b. So that's what makes it a secant line. And if we wanted to determine the slope of a secant line, well, that's just the slope of a line. So if I'm finding the slope of my secant line, in algebra 1, we might have said like y2 minus y1 over x2 minus x1. But in function notation, I would think of this ordered pair as being my ordered pair a comma f of a. And this ordered pair for our second point is b comma f of b. And so when we determine the slope, it's just f of b minus f of a over b minus a. We often call this a difference quotient, and a difference quotient, we know the word difference we associate with subtraction, quotient we associate with division, and a difference quotient is when we have division of subtraction. So when we're dividing things that are being subtracted, in this case f of b minus f of a and b minus a. So that's how we could find the slope of a secant line. But if we want to find the slope of a tangent line, we're going to have to do something a little bit different. So when we talk about a function, we could describe it as being locally linear at a particular point. And so what that means is like when we zoom in really close to that point, the graph will appear linear. So I'm going to literally zoom in. I'm going to just pick a spot on this curve. And if I zoom in really close, well, this is as far as I can zoom in, right around this point I just made, that graph looks linear right there. But when we zoom out, we can see that the graph of f is a curve and not in fact linear. So when a function is locally linear at a point, we can draw a tangent line, and a tangent line is determined by one unique point. So I'm going to redraw that point, and I'm going to say that this point occurs when x equals c. So our output would be f of c, and we could think of this ordered pair as c comma f of c. And if our goal is to first sketch our tangent line here, oops, okay, it's not very tangent looking, but let's imagine this is our tangent line. So it's really locally touching the curve in that one spot. I realized that it might actually intersect the curve again over here. That's okay, because we're really just looking close to our point C. and it's only intersecting our curve, it's only touching our curve once, really close to point C. So if I wanted to find the slope though, I really need a second point. So if we put a second point on our graph, let's imagine that the distance between these 2 points, we could just think of this as delta x, like this is our change in x. So this point, instead of calling it d or something, I'm going to think of this as c plus delta x. So wherever I was on my number line, c, plus my change in x to get to this new point. That means our ordered pair for this point is c plus delta x, comma, f of c plus delta x. And so if we were to find the slope of the line that goes between those 2 points, well, the way we're starting this off, that is still going to be the slope of a secant line because we're using 2 points. So again, our slope would be like f of c plus delta x minus f of c over c plus delta x minus c. And these 2 c's on bottom cancel out. So we really end up with just f of c plus delta x minus f of c over delta x. So I'm going to just go ahead and erase those since we canceled this out. Now again, this is not yet the slope of a tangent line. So what we need to do is we actually need to move this point to be as close as it can be to really be laying on top of our original point C. And if those 2 points are on top of each other, we'll get the slope of a tangent line. So to do that, that means we need to make delta x approach 0. We really need delta x to be 0. So how we can do that mathematically is with a limit. So we're really finding the limit of this, what was the slope of a tangent line, but we're finding the limit as delta x approaches 0. And that's going to cause those points to lie on top of each other, and that's going to cause our line to be a tangent line. So when we find the slope of a tangent line, or when we talk about the slope of a tangent line, that is what we mean when we say the derivative. So the derivative and the slope of a tangent line are, they pretty much mean the same thing. And it's such an important idea for us in calculus because we're going to be working often with instantaneous rate of change, which will also equate with the slope of a tangent line, as opposed to average rate of change, which we would associate with the slope of a secant line. So we could say that the slope of the line tangent to f at x equals a is called the derivative of f at x equals a. And we'll sometimes refer to this as the slope of f as x equals a, or the slope of the tangent line of f as at x equals a. So if the slope of f exists at a, we could say that f is differentiable at x equals a. So when we can take a derivative, we say our function is differentiable. If the slope of f exists for all values on an interval, we could also say that f is differentiable on an interval from a to b. If we say that f is differentiable, that means f is differentiable everywhere. So if we are not specific about an interval and we're told our function f is differentiable, that means that we can take its derivative anywhere that the function exists. So when we think about the definition of the derivative, we just talked about how to derive that. So we said our actual definition of the derivative is when we have 2 points, we're finding the slope of what would be the secant line, except that we are applying a limit to this so that our delta x, the distance between those 2 points, approaches 0. And that effectively makes this the slope of a tangent line. There's 2 different ways that we will see this commonly written, 2 different types of notation. The first looks like f with an apostrophe and then x. And this is called prime notation, and we literally read this as f prime of x. Another way that we will see this written very often, and these are interchangeable, so these mean the same thing, is We'll see this written where it looks like dy divided by dx. We literally read this as dy dx. And what that really means is the derivative of y with respect to x. X is our other variable. So for these first two examples, we are really just focused on writing the definition of the derivative. And this is the definition of the derivative. Again, it's not a definition with like words and phrases, but it is this limit right here. We're focusing on writing the definition of the derivative for f of x if f of x is x squared. And we're asked to do this specifically at the point of x equals 2. So if I'm finding the definition of, the derivative for f of x, I could use prime notation and I could say that this is f prime of x. And I might start out by saying, well, this is the limit as delta x approaches 0 of f of x plus delta x minus f of x, all of that over or divided by delta x. But for our function, we need to be more specific because we are given an actual function, f of x is x squared, and we are given a particular location on our x-axis to use, which is x equals 2. So out to the side, I might think of this, if f of x is x squared, I'm going to replace f of x with x squared in this part of my definition. But then that means that I also need to replace f of x plus delta x. So it helps me a lot to write this out to the side, that f of x plus delta x. Well, I'm going to take my function x squared, and wherever I see an x, I'm now going to make it x plus delta x instead. So f of x plus delta x is just the quantity x plus delta x squared. Those parentheses matter. I'm not going to distribute that. We could, but there's really no need. So when I'm writing my definition, I'm going to replace f of x plus delta x with x plus delta x, that quantity squared. And then finally, our delta x still just represents our change in x. So as we do kind of like our first rewrite, we're finding f prime of x. We could think of this as the limit as delta x approaches 0 of x plus delta x squared minus x squared, all of this over delta x. But we're still not done yet. We have one more piece to consider, is we were actually told to do this specifically for the value where x is equal to 2. Well, that just means that we're going to make all of our x's 2's, not our delta x. Delta x is not the same as x. That's our change in x. So what we're really finding, if I'm finding my derivative f prime of x when x equals 2, I could say that I'm finding f prime of 2. And this will be the limit as delta x approaches 0 of 2 plus delta x, that quantity squared, minus 2 squared, all of that over delta x. So this is how we could find the derivative of f at x equals 2, or we can call that f prime of 2. Now, right now, I'm not actually going to work out the long way to do this example. If we were to substitute 0 for delta x, you might notice we get 2 squared minus 2 squared over 0, which is 0 over 0. So anytime we evaluate the limit at the definition of the derivative, we're going to have a hole. We will always have a hole. So we can actually evaluate this by distributing and by removing our whole discontinuity, but we're not going to do that right now with this function. All right, our second example is to write the definition of the derivative of g if g is equal to e to the x. So we are not given a particular value of x to plug in here. So out to the side, I'm going to think if g of x is e to the power of x, I know the other piece I'm going to need for the definition of my derivative is g of x plus delta x. So again, just like before, I'm going to take e to the x, but wherever I have an x, I'm going to change that to x plus delta x. So now when we find the definition of the derivative of g of x equals e to the x, again, we could call that g prime of x. That's going to be equal to the limit as delta x approaches 0 of, so normally we would have like g of x plus delta x minus g of x, that quantity divided by delta x, but we want to be specific. So I want to plug in my function here. So e to the x plus delta x minus e to the x, all of that over delta x. So this is our specific definition of the derivative of g when g is equal to the function e of x. The notation can look a little confusing at first, and that's okay. But this is such an important topic for us in calculus, and we're going to use derivatives to understand rates of change.